Okay, so the big things we've discussed so far. We've discussed that whole idea of a dilution. And that dilution had a couple of applications. The one that we discussed last class was using a dilution to change the concentration of a formula. For example, let's say we wanted to go from a 60% concentration to 10%. The dilution required was just the new percent over the old, or the diluted percent over the concentrated percent, which reduces to 1/6 or a 1 in 6 dilution. And if you recall, if we were mixing that, a 1 in 6 dilution, the 1 is the concentrate, so that'd be the 60%, and the 6 is the total volume. So that means if you're adding sterile water to that, or saline to that, it would be a 1:5 ratio of the concentrate, the 60%, to sterile water. Excuse me, I'm losing my voice today, so I struggle through. Then we looked at a shortcut formula for changing this, where we're given a volume. Let's say we have 200 milliliters of a 30% solution. We're going to dilute this to 800 milliliters. Find the new concentration. So, our formula for this was V1 times C1, the initial volume times the initial concentration, is equal to V2 times C2. Final volume times final concentration. So we have 200 milliliters times 30%. That's going to equal our new volume. Oops, I figured a zero there. It's supposed to be 800 milliliters. So 800 milliliters times our new concentration. So 200 times 30 is 6,000. We divide by the 800. We get 7.5 is our new concentration. So 7.5% is the new concentration of that solution. Well, today I want to take a peek at the different ways of defining that percent, or that concentration. At least we're going to start out with that. The most common way that those are defined from what we've done so far is a V in V, or what's called a volume in volume concentration. So in a volume in volume concentration, the serum is measured in volume, and of course the dilutant, or the water is the solvent, is measured in volume as well. In a volume in volume, what we are comparing is the volume of serum to total volume. Now, this may or may not be the sum of the two volumes. Since most medications is technically a solution where the one substance, the serum, is dissolved into that solvent, the volume does not necessarily increase additively. If I have 40 milliliters of serum and I add it to 80 milliliters of sterile water, I do not necessarily get 120 milliliters. What happens is some of those particles of the serum actually will hide between the particles of water. Now, you don't think of water as having space in between it, but it does. If you add 40 milliliters of salt, 80 milliliters of water will give you kind of a high concentration, but if you add salt into water, if you measure the volume of the salt and the volume of the water, if you add it together and stir it up and dissolve the salt into solution, the total volume you'll get is not going to be the sum of the two volumes. It's going to be much less than that. So when we're looking at this, we have to be very careful that we're looking at the total volume after the serum is dissolved into that solution. So the wording we'd be looking at would be something like this. Let's say we have a 1,200 milliliter solution, contains 300 milliliters of serum. Find the concentration. Well, we are still working with a percent, so it's going to be blank over 100 equals our serum, 300 milliliters, over our total volume, which is the 1,200 milliliters. But notice this 1,200 milliliters of solution, not 1,200 milliliters of water or saline. It is 1,200 milliliters of the total solution. Cross multiply and divide here. 100 times 300 divided by 1,200 gives us 25. So that is a 25% solution, or 25% concentration. The second way we look at it, the W and W, or a weight in weight concentration. For weight, we are also looking at the weight of the serum over the total weight. However, weight is additive. The total weight is equal to the weight of the serum plus the weight of the solvent. In most cases, sterile water. So in this case, we can look at these problems in one of a couple of different ways. We could have 40 milligrams of medication is combined with 600 milligrams of saline to create a solution. If we're looking for the concentration of this solution, again, our concentration is a percent. This is going to be 40 milligrams over, on bottom here is going to be the 600 milligrams of saline plus the 40 milligrams of the medication. So that's going to be 40 over 640. We'll cross multiply and divide. 100 times 40 divided by 640 is going to give us 0.0625, so 6.25%. So that is a 6.25% or 6.25% concentration. Now the weight and weight concentrations might also be given as an 800 milligram solution contains 120 milligrams of medication. To find the concentration of this one, we are looking at 120 milligrams of medication. Now the 800 milligrams is the total solution. So it's just going to be that equals blank over 100. So you cross multiply and divide. 100 times 120 divided by 80 is 15. So that is a 15% concentration. It is not very often that we measure concentrations, however, as weight in weight, because we don't usually measure the amount of a solution in milligrams. The amount of a solution is almost always measured in volume or milliliters. It is sometimes used the volume in volume, where we'll measure our serum in volume. The volume in volume is most likely used when we already have the medication in solution. Now, if we already have the medication in solution, it's most likely already in some sort of a concentration, some sort of a percent concentration. So that means we're not really using a volume in volume calculation. We're using a dilution to dilute it down to a lower concentration. So the volume in volume, while a little bit more common than a weight in weight, still is not horribly popular. The most common concentration we look at is a weight in volume. Now, to make a weight and volume concentration work, we first must define the units. For the other ones, a volume in volume or a weight in weight, as long as we're using the same units for both of them, milliliters compared to milliliters, or fluid ounces compared to fluid ounces for volume and volume, or milligrams to milligrams, or micrograms to micrograms for weight and weight. As long as we're using the same units for both substances, for both measurements, the concentration works out. For weight and volume, obviously, we can't measure weight in the same units as we measure volume, so we have to define what units we're going to be. In the metric system, 1 gram is defined to be the mass. I know we're talking about weight here, but remember we use mass in place of weight for conventional calculations in the metric system. 1 gram is defined to be the mass of 1 milliliter of water. And since we're diluting most of these with water, or saline, which is the same density as water, we're going to use this equivalent. So our weight is going to be measured in grams, and our volume in milliliters. So 1 gram and 1 milliliter are relatively close to being equivalent. So let's say that we also, by the way, for volume, we are just using the volume of the water in this case, or the saline. In most cases, with a powder being added to it, a majority of the volume of this is usually a powdered medication being put into a solution. The volume of the powder does not significantly change the volume of the total solution because, just like we said before, it hides between the particles of the solvent. So anyway, let's say here we have 3 grams of medication combined with let's go with 60 milliliters of saline. We find our concentration here. This will be 3 grams over 60 milliliters. I don't want the R on the grams. 3 grams over 60 milliliters. And of course, this will be blank over 100. We cross multiply and divide. We get 5. So this is a 5% solution. We might have 400 milligrams of medication. Combined with 120 milliliters of saline. Finding that concentration, well, we're not going to use the 400. We need to convert that into grams. 400 milligrams is going to be 0.4 grams. So that's 0.4 grams over the 120 milliliters. Turn that in percent, so how much out of 100? So 100 times 0.4 divided by 120. Was that 2.5? Let's double check it. Oh, sorry, 3.33. So it's 3 1/3 or 3.33% concentration. So that is how our concentrations are initially calculated. And of course, the dilutions can adjust them down from there, or we can use that concentration adjustment formula. Once we have these mixed and we calculate a dosage, we somehow have to deliver that dosage to the patient. So the next thing we're going to look at is if it's well, there's 2 ways that a liquid medication is normally delivered to the patient other than orally. There's an injection, which is often called a bolus. A bolus is nothing more than an injection that goes through an IV, but it is directly given, and then there's just a direct injection. Both of these are one-time injections. And that requires a syringe. Now, the other way that it can be given is it can be given through an IV drip. This is something we're going to talk about more on Friday's class, calculating how that's going to be. That is done over time. So it's a consistent, steady administration of the medication over a period of time. So what we're going to be looking at right now is these, and by one time, I mean it may be all at once, and it may be given regular intervals. It may be every 4 hours or every 8 hours, but all the medication is given at a single dosage each time and not spread out over time like in an IV. So even though the bolus is injected into an IV, it's injected in a way so that it goes directly into the bloodstream all at that single time. So let's take a look at how we load a syringe if we have a given dosage. First thing we need to do, here's my version of what a syringe looks like. Close enough. First thing we need to do is we need to determine what the markings of the syringe stand for, what the scale of that syringe is. So to do that, we have to look at the labeling on it. We might have something like this. This is labeled, let's say it's labeled milliliters, 1, 2, 3, and 4 for now. First thing we need to do is figure out what each of those markings represents. Go from here to here. Generally, I do not use the first part of the syringe. The main reason for that is generally this end here is tapered just a little bit to allow for the shape of the plunger. So the first 1 or 2 markings on the syringe are often unclear. To figure out what each marking represents, we have to figure out between 2 locations that we know the value of, the volume of. We have to figure out how many markings are in between there. So we're going to go here. This one we know is 1 milliliter, and this is 2 milliliters. We're going to count in between there 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 divisions. And of course, the value represented by each division is equal to the difference in the 2 volumes. So in this case, 2 milliliters minus 1 milliliter, which is equal to 1 milliliter, over the number of divisions, so 10 divisions. 1 milliliter divided by 10 is 0.1 milliliters per division. So on this particular syringe, each division, each marking is 0.1 milliliters. So let's say that this is filled to right here. Well, first I can tell by this that this marking right here is 2.5, because it's halfway between the 2 and the 3. And each one is 0.1 from there. So this would be 2.6, 2.7. We have 2.7 milliliters. Let's say one is labeled slightly differently. Let's say this one's still labeled milliliters here. This is now 1 and 2, like that. So again, I'm going to choose spots, not at the beginning here, but 2 spots where I know the volume. I have 1 milliliter and I have 2 milliliters here. Between there, if I count up the spaces, now I'm not going to count all of those. What I'm going to do is I see that we have 4 equal pieces here. If I count up how much is in one of those, I can just multiply by 4. I have 1, 2, 3, 4, 5 times 4 is 20 divisions, or 20 spaces. And again, I have 2 milliliters minus 1 milliliter divided up over 20 divisions. So that's 2 minus 1 is just 1 milliliter divided by 20 divisions is 0.05 milliliters per division. So let's say that I was going to fill this syringe up to here. Now I can see, let me erase some stuff here. I can see that between 1 and 2, there are 4 of these equal spaces. So I know that this is 1 1/4 or 1.25. This is 1.5 milliliters. Each division beyond that is 0.05. So this one is 1.55. This next one, 1.60. So that syringe is filled to 1.6 milliliters. Now the next issue I want to write, I'm going to label this one here. I just want to label a couple of them here. We're going to make a choice. It's labeled in milliliters. This one's also labeled in milliliters. And let's say that we have a required dosage now of 0.6 milliliters. Both of these syringes are capable of administering 0.6 milliliters. Does it make a difference which syringe we use? Well, at first thought it might be no, but there's a definite difference between which one we use in this case, because we want to look at the potential error. No matter how careful we are, you're never going to load a syringe exactly. Now the difference between these two syringes is the one here that gets to a larger volume faster is generally a wider, a fatter syringe. So that syringe probably looks more like this. Whereas the one that has the smaller numbers or doesn't get up to as large of a total volume is most likely a thinner syringe. So I'll put that in a different color and I'll put it inside here. Most likely something like this, a little bit narrower. So let's say that we go to load this, and let's say here is the spot that we're shooting for. I'm just going to draw a line straight across there. So that is the marking on the syringe that we want to get our exact dosage. And let's say that we are just a little bit off. Let's say we pull a little bit long. So our plunger is a little bit past where we want to be. Not a huge difference, just barely past. Well, if we look at the smaller syringe, the green one here, where the numbers were what smaller numbers, the amount of medication that we are off is this amount right in here. Obviously, that's a circle, not just a rectangle. So actually, it's a small cylinder in the syringe. The volume of that is very, very small compared to the volume of this whole thing here. So on the fatter syringe, or the syringe that goes up to the higher numbers, like this second one here, being off by the same distance is a larger volume of medication. Up here, of course, since that's a thinner syringe, I realize these are all the same size, but a thinner syringe being off by that distance is going to be a smaller volume of medication. So the general rule is it's more accurate to have a full syringe. The fuller the syringe is, generally the more accurate it is. Now that doesn't mean you want to always just use the thinnest or smallest syringe you have, because you want to make sure that you don't have to inject a patient twice for a single dosage of medication. So in this case, we have 0.6 milliliters. Well, on this one, there's a marking on there that's 0.6. So you just fill it right up to that marking. If we were in a situation where we had to use this syringe to do it, once again, we'd have to figure out the amount per marking. We've done that here. Each of those markings is 0.05 milliliters per division. We can look between the 1 and 2 here and realize each of these major divisions is a quarter of a milliliter. So that would tell us this one here is probably 0.5 milliliters. Going up from there, we've got 0.55 and 0.60 milliliters. So we would fill it to that point. And again, you can see this syringe here is only about a quarter full, while this one here is about 2/3 full. This is a much more precise dosage. So let's look at a couple more here. Let's see if you can read these. So on this syringe where it's labeled in tenths of a milliliter, I am going to fill it to this point right here. Take a second, see if you can figure out what that volume is, if you can see it close enough at your location there. So if I were figuring this out, I would pick 2 points where I have a known volume. So I have the 0.1 to 0.2. So I'm at 0.2 milliliters minus 0.1 milliliter is a difference of 0.1 milliliter. Over, there are 10 divisions there. So each division is 0.01 milliliters. So over here, this is 0.31. 0.32, 0.33, 0.34 milliliters of medication. So on this one, let's say that we are filled to this point here. So once again, find out from here to here, that's 2 milliliters minus 1 milliliter, or 1 milliliter of difference, spread out over 10 divisions. So that's 0.1 milliliters per division. This is our halfway point, which is 2.5, 2.6, 2.7, 2.8 milliliters. Anybody have any questions on those? Okay. So, the next step then is to talk about the dosages. We have 3 methods that we're going to use for dosage calculation. See how long my voice hand holds out here. We're going to start out with a dosage calculation formula. I'm not a big fan of the dosage calculation formula. The book uses it. To me, it's clumsy and it's awkward and it's a little bit confusing as to what each of the pieces are. But here's what the formula looks like. D over H times V equals A. Where D is the desired dose, or the doctor's orders. So the ordered dose. H is the on-hand dose. V, which is the part that's always confused me, is the vehicle. The vehicle is what carries this on-hand dose to the patient. If it's a tablet or a capsule, let's say it's a 200 milligram capsule, the vehicle that carries that, the on-hand dose would be the 200 milligrams. The vehicle that carries that 200 milligrams to the patient is 1 capsule or 1 tablet. And A, that is the dosage that is going to be administered to the patient. So let's take a look at an example here. Let's say the doctor's order is for 500 milligrams. On the bottle, the label says 200 milligram tablets. So for our formula, D is the ordered dose. That is 500 milligrams. Now, part of the key here, this ordered dose and the on-hand dose must have the same units. So if I'm using the dosage calculation formula, that's one way I can figure out what the on-hand dose is. Well, the only thing here that has the same units as the 500 milligrams in the doctor's orders is the 200 milligrams. But you might be looking at that thinking, but the 200 milligrams was tablets. And that is true. 200 milligrams per one tablet. One tablet is our vehicle, because it's that each tablet or one tablet that carries that on-hand dose of 200 milligrams to the patient. So now we divide out. 500 milligrams divided by 200 milligrams. Milligrams divide out. 500 over 200 is 2.5 times one tablet is 2.5 tablets. So 2.5 tablets is what is administered to the patient. Well, let's say we have an order for 400 milligrams of medication. And let's say on the bottle we have a liquid medication here, a solution that says 25 milligrams per 2 milliliters. So now, looking at our dosage calculation formula, our ordered dose is the 400 milligrams. Below that's going to be the on-hand dose, and this usually comes off of the label of the bottle. The only thing there that's in milligrams is the 25 milligrams, which leaves us with the 2 milliliters that must be the vehicle. Again, that's always been a little bit confusing to me, but you have to look at it as the 25 milligrams is the medication or the amount of medication that matches up with what's ordered. What carries that 25 milligrams to the patient is 2 milliliters of solution. So again, 400 milligrams divided by 25 milligrams. Our milligrams cancel out, and that is what, 16? Because 16 times 2 milliliters is 32 milliliters that is administered to the patient. That is the dosage calculation formula. We'll do more examples on Friday, partly because I want you guys to work with some of the dosage calculations and figure out which of the three methods that you prefer. The dosage calculation is my least favorite method. My second favorite method is the next one here, which is the proportion. In the proportion method, we start with the label on the bottle, or the medication itself. Usually that is the on-hand dose and the vehicle combined together, but we don't necessarily have to define them in those terms. And what we're going to be doing is we're equating that to the doctor's orders, either top or bottom, with what we're going to administer. So let's take a look. So let's say we have a doctor's order for 800 milligrams of medication. The label is 250 milligrams per 4 milliliters. So our proportion starts out with the label here, 250 milligrams per 4 milliliters. Now, one of the nice things about the proportion is the other side of this sets itself up. Because in a proportion, whatever units we have here, we have to match up the units here. So over here, this must also be milligrams. The other thing we have as milligrams is the doctor's order of 800 milligrams. What we're going to get down here will be milliliters. We're going to cross multiply and divide. 4 times 800 is 3,200 divided by 25, or 250 I should say, gives us 12.8 milliliters of medication. That is what will be administered to the patient to give them the 800 milligrams. Or, similar to that, we might have an order for, let's say I have an order for 1,400 milligrams, and the label or the bottle says 500 milligram capsules. This is a little bit more difficult to figure out what the initial ratio is, but it is 500 milligrams per one capsule. On the other side, we match up. 1,400 milligrams has to go with the milligrams. So this is going to have to be capsules down here. Cross multiply and divide, we're going to get 2.8 capsules. Now we'll talk about rounding later. Capsules, of course, you're going to have some partially filled capsules if you want part of it. If it's tablets, tablets can either be scored in halves or quarters. So if it was a tablet, you'd have to round either to the nearest half or the nearest quarter. We'll talk about that later as well. For right now, we'll settle for just getting 2.8 capsules. Our third and final method is a unit conversion method, or what the textbook uses the fancy word, dimensional analysis. And all it is basically taking what the doctor is ordering and using the label on the bottle to make a unit conversion. It looks very similar. If we just looked at the setup, it looks very similar to the dosage calculation formula. It's just a lot easier to set up for me. So let's say we have a doctor who orders, excuse me, 700 milligrams of medication, and we have a label that says 200 milligrams per 5 milliliters. So we're going to start out with the doctor's orders, 700 milligrams. Now, Friday we're going to look at IV flow rates, where the dosage is going to be a rate in itself. It'll be so many milligrams per hour or drips per minute or whatever. And so it'll already be a ratio or a rate. In this case, it's not. It's a single number, so we turn it into a rate or ratio or basically a fraction by simply putting it over 1. Just like we did if we were converting, pounds to ounces or something like that. Now, we're getting rid of milligrams, and we're going to convert to milliliters, because we're going to administer this liquid medication measured in a syringe to milliliters. So using the label, 200 milligrams to 5 milliliters. Now notice that's upside down, but to make our unit conversion work, we have to match up so that the milligrams will cross cancel. So then 700 times 5 is 3,500 milliliters over 200. Dividing that out is 17.5 milliliters of medication. Okay, we're running really short on time, so let me give you your homework. In the book, page 146, 1 through 17, the odds, covers the concentrations. Page 153 through 154, 1 through 15, talks about the syringes. Page 162 through 163, 1 through 23 is starting the dosage calculation formulas. And page 168 through 169, 1 through 19, is dealing with constituting a solution and stuff like that. You can do the odds in each of these, by the way. I just wanted to make sure we didn't get cut off before I got them up here. So with that, I'll wish you guys a good day, and we'll see you on Friday.